Hello, listeners, and welcome to the third episode of the Semi-Doped podcast. I am Austin Lyons with Chipstrat, and with me is Vic Shaker from Vic's newsletter. All right, so this week was CES, and of course, we had a big, long presentation from Nvidia, as always, and we want to unpack that and just dive deep, give you our thoughts, some interesting strategy insights and technical insights, and I'm going to start with Vic, our technical guru. So, Vic, what stood out to you?
Hey, Austin. Yeah, this CES was like, where's the consumer equipment here? There's like nothing that we can use at home. Why is it a consumer electronics show? You're showing us all these like Vera Rubin platforms that I can't put in my house. I can't even buy one of those Grace Blackwell chips or Vera Rubin chips. I mean, why are you showing this to me? Anyway, it was like the first time it appears in 5 years they haven't introduced any GPUs at CES. So that was interesting. However, what I took away from the whole thing was when Jensen brought on those like cute robots, and I'm like, how much for one of those things? I just want one of those, so I could just like wander around my house, like super cute, you know. They're like Jensen pets, Nvidia, NV pets. You know, I want some NV pets for myself.
Yeah, there's consumer electronics for you.
Yeah. I mean, and then he goes on to declare that this is the ChatGPT moment for physical AI. And I'm like, yes, give me a cute robot and I'm good to go. Anyway, that's before we get into talking about all this enterprise Vera Rubin stuff. What did you see that was even remotely consumer based?
So something interesting that I've been noodling on, and I just wrote about this, the DGX Spark is within the consumer price range or the home tinkerer. And for anyone who hasn't been following along super closely, you may remember Project Digits a year back or so, where Nvidia said, hey, we're going to take a server grade, cloud grade AI supercomputer like Grace Blackwell, and we're going to bring it into desktop form so it can actually sit on your desk. They had a naming contest, and they ended up naming it the DGX Spark. And this is a GB10 chip is what they call it, Grace Blackwell 10. So it's definitely slimmed down from the GB100, but it is truly bringing NVIDIA's server architecture to the desktop. And so this could be thought of a little bit as consumer electronics in that it may be the first time you could actually have true AI PC server really within reach. So that's the closest I can get to a consumer electronics play.
What do you think that a person who is a consumer, an enthusiast, would want an AI PC at home for?
In the CES presentation, NVIDIA did have a video, and I thought it was really awesome. And it was a dev sitting down at his desk and hacking on a personal project, which, by the way, the first thing that stood out to me right there is if you look closely, he was on a MacBook, and the DGX is sitting on his desk, and it's plugged in. Of course, it's air-cooled, and it's connected to the internet, so it's not like a huge liquid-cooled beast. But he was using his laptop as a thin client. And he was running a server, basically like a little chat interface server, so he could, have his own little local chat bot. And then he set up a router where he could direct queries to different models. So like text queries to a fast text model, but he also connected it to a robot so he could ask questions and have it routed to the robot, which of course has a camera. So he could ask questions about his environment, like, hey, where's my dog at? Is it on the couch? And what he did was he set up on the DGX Spark this router that could say, oh, that's asking an environmental question that needs visual information. I'll send it to the robot, have it grab a picture, and then give that image to a vision language model, a VLM, running on this DGX Spark. And I would be able to answer the question like, hey, is your dog on the couch? And he shouldn't be. And then, of course, you could give it a command like, hey, tell my dog to get off the couch, right? So you could route, again, the DGX Spark could route it to the robot, and the robot could use its speaker essentially to talk to the dog. And what I thought was really cool about this is like, oh, this could be what the AI PC actually is, where you're hacking around, creating really interesting things. Honestly, it reminds me of IoT when everyone was like, hey, now I can make my lights turn on and my garage door close and stuff like that when I wake up or when I go to bed. But you can imagine it being even more interesting and even easier to program because you can just use language models to talk to it. And anyway, so I thought this was actually a really cool demo of where I could see, like, I could imagine people hacking at home again, whether it's IoT or other interesting things, or definitely at work, having access to this and being able to say, like, I truly want to automate some of my workflow. How can I use a DGX Spark or something like that to help me do that? So yeah, what did you think about the DGX Spark?
It was cool. I saw the pictures on like X. It had this like, picture of this chip with these like liquid cooling in it and all that. It's not like the server grade thing, but anyway, it was very sleek, black looking thing that was awesome. And I was like, wait, what is the power consumption? Do you know any numbers of how much this would run at home? Because this is going to be a power bill nightmare otherwise.
So, okay, good question. So there's two different products here. There's the DGX Spark, which is this little tiny form factor mini PC thing. And then there's the DGX Station, and that's what you're referring to. And like Dell had one, and there's pictures on, like, go to Michael Dell, on X, and you can find it where the side is taken off. And it's literally looks like a desktop computer of old. But yes, you can see like copper cold plates in there and like what appears to be maybe tubing. And so like it might be liquid cooled, which now that product, by the way, has some sort of GB300 chip in it. There wasn't many details. Nvidia's DGX Station was like a sort of a reference design. Then Dell took that and made the Dell Pro Max. And for listeners, this is your GB300 chip. So straight up, this is server grade Grace CPU, Blackwell GPU. It has HBM. So it was like in the Dell's instantiation of it, it was 784 gigabyte of unified memory. It was 288 gigs of HBM3 and then 496 gigs of LPDDR5. It's the NVLink chip-to-chip coherent memory, like literally, if you're a developer who used to have to do all of your local development, if you will, actually just remoting into a cloud to access a GB300 there, now you literally can have that at your desktop. But I will say to your question, Vic, I'm thinking like, okay, if this is like 1500 watts or something crazy of power dissipation, which by the way, the DGX Spark is like X less. It was on the order of like 140 watts. If we're talking like 1500 watts of heat dissipation, and if that's truly liquid cooling, I'm not sure how that's going to work at my desk at home.
Yeah. So I looked it up while you were explaining this. I saw all the specs of this thing, and you hit the nail on the head. It's actually the system power for the DGX Station, 1600 watts.
Oh, wow.
So it is quite the beast. And I think it's aimed more towards an enterprise level deployment where you could have a smallish inference server that is running HBM, serving multiple users and things like that. Maybe it's not really meant for the, home hobbyist, but that's what the DGX Spark is for.
Yes. Okay. So, I was writing about this too, and I've been thinking about this, and I think you're exactly right. DGX Spark, that's going to be on the order of like $4,000 or something. That's, definitely like high-end hobbyist or still useful at work, like totally useful in the enterprise. DGX Station, the way I'm framing this and thinking about this, it reminded me back of the 1960s era where people had big IBM mainframes that cost, $1 million plus. And at the time, and remember, this is 1960s, right? So at the time, there weren't that many actual enterprises who could afford it, but the ones who could, wow, you got access to frontier compute. That's amazing. Then we started to see the rise of the mini computer, which was like 10x cheaper. Mainframe class compute, but now all of a sudden it's like 100K. And that actually expanded the total compute TAM because now suddenly large enterprises, mid-size enterprises could buy this. And of course, as these form factor, they're still big, but not mainframe big. But as the form factor shrunk over time and the cost came down a little bit over time with competition, you could literally have a mainframe at your desk. You could literally have individual teams that had their own mini computer instead of one big mainframe shared across the whole company. And so when I've been thinking about the DGX Station, I've been thinking about that as an analogy of like, hey, today, if you want a rack of AI compute, I hope you have 3 million plus, and again, maybe also a liquid cooled environment to put it in or whatever, like hyperscalers do, and some very large customers do, but a lot of people don't. So they're still stuck renting GPUs, or they're just locked out of having AI supercompute. But there's latent demand there. And so when I think about the DGX Station, I think about you can literally get a Grace Blackwell, and instead of needing 7, you can have 1. You can have 1, and I don't know how much it's going to cost. Is it $50,000 for the Dell Max Pro. Is it $100,000? I don't know, but you can unleash the supercomputer from the hyperscaler cloud, and you can actually put it in your building. And I don't even think, if it's liquid cooled, like to the point, the form factor looks like a desktop that you could put at your desk, but maybe you're still actually just putting it in your on-premises environment where you already have some cloud, or like not cloud, but some local AI compute racks with like CPU servers or something. And so maybe it's like in a closet or in a back room somewhere, but you're taking the AI supercomputer, unleashing it and putting it in your own business. So now all of a sudden, maybe mid-sized enterprises can afford one or multiple. And to your point, I envision, like, why not run a bunch of local inference on it? Like, I don't think of it as necessarily only like a very beefy, very expensive single dev ML researcher workstation. I actually think these, you could call them like an AI appliance, if you will, like local AI appliance, could sit in a room and actually serve all sorts of interesting inference for local use cases, especially if you want to have your own private data, or you just don't want it accessing the outside world or whatever. You just want to have control over it. Why not just run that locally? And by the way, of course, I think CFOs would be super interested in this, because now they're thinking OpEx of renting GPUs converts into CapEx. Like, there's all sorts of interesting benefits here.
Yeah, absolutely. And that's the nice thing about things that were mainframes becoming a computer on your desk today, because the phones that we have today are an extension of that, because these mainframe-like computing powers are now in our phones and pockets. So in that same analogy, maybe in the future, we'll have phones that can run complete inference, or watches that can run complete inference. Maybe that is the use case for edge AI. And maybe we're not just there yet, and it takes time to get there. But you see how, your argument went stretched to the extreme on the AI inference front can go to edge AI devices in a very nice way.
Totally. And in the interim, someone's going to ask, oh, okay, well, the counter argument is like, oh, are you going to actually put HBM in your watch or your phone? That sounds pretty expensive. But I do think we could live in a world right now where maybe you don't need to, because maybe if we have access to these like inference servers at work, I mean, maybe we can, again, use our laptop or our phone as a thin client. And as they showed in this demo, which everyone should go watch, there's like a 2-minute video you can find on YouTube. And until it becomes like cost acceptable, or the thermals get figured out and all those implications, maybe the AI that we run locally on our laptops and on our phones is still more of like the real-time speech recognition, real-time stuff. And then maybe this heavier like agentic stuff, you can still launch it from your phone or your laptop, but it's actually still running on some plugged-in compute, but it just happens to be cheaper and locally accessible.
Yeah, that's awesome.
Time will tell. Yes, folks, check out DGX Spark, check out DGX Station, go read my article on Chipstrat, noodle on it, because it is super interesting to think about this additional compute TAM by bringing the supercomputer to the desk. And you might ask, is this going to cannibalize some cloud use cases? And I would actually say, in the aggregate, no. Of course, yes, there will be some, but I actually think there's a lot of interesting new workflows that could run locally that are just accretive to everything you're going to already do in the cloud. Because think about it, the cloud is always going to be frontier compute, and it's going to run the frontier model. And what we run at the edge is actually like the frontier model from 5 years ago, as it has trickled all the way down. So to do the most interesting, most demanding stuff, long form video generation, whatever, you're surely going to still need racks of GPUs to do it. But over time, we will continue to improve in the amount of AI that can be done locally. And so I think there's just new interesting use cases waiting to be unlocked. Now, enough there. Let's move on. So consumer electronics. One other thing that you could start to call consumer electronics would be the car, right? Is the car not like a Rivian or a Tesla? Is it not just a computer on wheels? So I'm stretching here a little bit, but was there anything from NVIDIA around autonomy or automobiles, Vic?
Yes, Alpamayo. So Alpamayo is NVIDIA's answer to fully self-driving vehicles, kind of the ones that you find on Tesla vehicles, kind of. It is what they describe an open source autonomous vehicle platform that uses something called a vision language action model. So the way a vision language action model works is basically it takes sensor inputs from the environment and then it processes it through kind of a language model in the sense of it's going to do reasoning and chain of thought reasoning. And I'll explain a little bit more of what these kinds of things do. And then it takes action. So the action is basically in the form of trajectories or the list of possible actions that it can take in the future. So those are, the kind of decisions it needs to make based on the vision inputs it gets from its sensors, right? So the VLA model is actually a 10 billion parameter model. The way it works is it takes all the sensor inputs and it uses the LLM under the hood to kind of think through how a human would think through the whole situation. And there were like a couple of like videos on this as well that was really nice at the keynote. And it basically thinks through with the way you and I would, maybe if we speak out loud while driving, this is how we would be like, or telling our, if when our kids get old enough to drive, they'll be like, okay, this is what we would tell our kids. Hey, look out for the dog that's on the left. Make sure that you are ready for when it runs across. Or, hey, slow down, there's somebody crossing the road. Or accelerate because the light just turned yellow and it's safer to accelerate than slow down. So, these are the instructions that you would probably give with language to somebody you're teaching or somebody you are, or even maybe to yourself if that's how you drive. But that's what the VLA model does. This whole thing is going to be first tried out with Mercedes Benz CLA and is apparently hitting the roads in Q1 2026. So I don't know, if you see one, let me know. It's kind of cool. In response to all of this, I think Elon said like, oh, this is great. And actually to Jensen's credit, he did acknowledge Tesla as like the most advanced driving model on the road today. And so Elon was like, yes, this is good, but it's the getting it to 99%. That is the easy part, but handling all the long tails of self-driving, which is when you say long tails, if people aren't familiar with the phrase, it's all the unknown unknowns. Basically, you just don't know what's going to go wrong on the road. So there is a whole bunch of scenarios which you just cannot account for. And that's the hardest part of self-driving. And Elon says that is the part that has taken the most time to actually get right. And that's at least a few years away. So people are like saying, okay, Alpamayo is still like maybe a few years away from where the Tesla self-driving is today.
Yeah, definitely. There's a ton that we'll have to unpack here in its own episode. But I definitely was interested to hear that there was this Mercedes-Benz car that's going to hit the road. So obviously, oh, and one other thing, somewhere, I can't remember if it was, I think it was in the CES presentation, Jensen said something like they have a quarter of their company working on, it was some large number. Maybe it's just like 7,000 people, but some very large amount of people working on autonomous vehicles. I'll have to go find that somewhere to figure out what the exact number was, but it was a surprising amount of NVIDIANs, if you will, working on autonomous vehicles. So I think we'll only continue to hear more on this front, especially if Jensen thinks, it's the Chat GPT era of physical AI and self-driving is nothing but physical AI.
Yeah, absolutely. I think we will hear a lot more about this going forward. And they have this whole thing that is, the interesting thing about all this is all open source. And I was reading the website and they said, they have this entire data set of all, driving scenarios and vehicle dynamics. All of this stuff is actually on GitHub. So if you go to nvlab/alpasim, you will see like there's like a whole lot of stuff that you can use to do your own kind of like work on autonomous driving if people are into that kind of research. Not saying I can particularly do it, but it's amazing that they put all this out there for people to work on and improve. Obviously, it's a pretty hard problem.
Get yourself a DGX Station, download this GitHub repo, and off you go.
Done.
All right, should we move on to the Vera Rubin platform, even though it's not consumer electronics?
Yes, we should do it because, the bulk of the whole keynote talk was the Vera Rubin platform. And it was pretty amazing, honestly, I have to say. The Vera Rubin platform actually consists of 6 chips, right? It has the Vera CPU, the Rubin GPU, and they have a data processing unit or DPU, which is on its generation 4 Bluefield DPUs. They also have an NVLink switch, which is now on version 6 for scale-up networking. NIC, which is network cards for, networking within and outside the rack and the chips and all that. And then you have the Spectrum 6 Photonics, the first Photonics, Ethernet switch for scale out and in between racks. So all of this, like 6 of these things make up the Vera Rubin platform. And the fundamental claim is that the Vera Rubin platform provides a cost per token of 1/10 that of Grace Blackwell.
Let me quickly add in one thing. What's interesting is that NVIDIA used to say they made 7 chips. So they say, hey, we're not just a GPU company. We make 7 chips and write software, of course. And now they're saying 6 chips. And the one that's missing is the InfiniBand switch. So normally it was CPU, GPU, DPU, NIC. And then it was, we make 2 switches. One is Ethernet, Spectrum X, and one is InfiniBand switch. And here they specifically did not call out the InfiniBand switch. So I just found that was interesting. I don't know. I don't necessarily know that that means that they are going to stop making InfiniBand, but I think it does go to show that their customers have all been opting for Ethernet-based switches for scale out because people are familiar with Ethernet. And therefore, at a minimum, from a marketing perspective, they're just going to focus the conversation on that. So there's just one little interesting observation.
That's a great one, actually, because maybe this is a subtle hint of where things are going in the future.
Totally.
Yeah, let's talk about some of these chips. What do you think?
Yeah, I mean, let's dive in for people. We'll get a little technical here, but we can explain why it matters. But yeah, what did you hear from Vera and Rubin, and maybe how did that compare to Grace Blackwell?
Yeah, the Vera CPU actually has more cores than the Grace CPU. And interestingly, this is the first CPU from NVIDIA that uses their custom Olympus cores, which have been like in-house customized. It's ARM based, but it's ARM compatible. But it's not an off-the-shelf ARM core like their previous generation Grace CPUs, which actually used 72 ARM Neoverse cores. So there are 88 custom cores now versus the 72 ARM cores in Grace. So that's the one big difference. And this Olympus core actually supports spatial multi-threading, which means it takes in 2 threads per core. And therefore, now you effectively have this is basically the multi-threading thing we saw with CPUs like in the 1990s or 2000s or wherever that came out. So now you have 176 threads running actually. So the real jump is from 72 to 176, which is kind of significant when it comes to computing power on the Vera CPU.
Interesting. Why does that matter for a GPU? Because at the end of the day, all the matrix multiplications are happening on the GPU. So, but what's going on the CPU, and why is even more simultaneous compute useful?
So the CPU is used for a lot more stuff than just matrix multiplication, because in the era of AI agents, that the year 2026 is supposed to be all about agents, there's going to be a lot more CPU based interactions. So for example, if you give a command to do some task to an agent, the agent has to decide which tool has to be invoked and how to collect data from the tool and how to feed it into the next tool, and so on and so forth. And, it has to access a database if required. It has to pull data. It has to decide when to send it to the GPU for matrix multiplication. And, all of this, orchestration processes and compression. You need security, so you need to encrypt. So all of these functions are handled by the CPU. And the more agentic the workload becomes, the more CPUs you're going to need and the more horsepower you need in CPU land. So that's why this is important.
Yes, that's where my head was at exactly, which is if you go way back, at first the CPU was like, maybe the Hopper era, it was a little bit more of like a glorified memory controller. It was just about like, how do I get the right data pre-processed, shaped, and ready for the GPU to keep it fed? And then we started to see like the rise of RAG. And so like, oh yeah, how do I have like all my internal documents in a database so that as we are querying something that could be hallucinating, we can ground it against this database query and with actual relevant context, essentially. And so it's starting to put more onus on the CPUs. And to your point, like as we get into an agentic era, there's going to be all sorts of orchestration, security, even potentially like you have to ask, where's like user management and all that stuff going to live? Is it going to live on that head node CPU or is it going to live somewhere else? I think TBD on that. But I think your point is still right, which is with the rise of agents, there's going to be more and more demand put on CPUs. And so, of course, zooming way out when we're talking about Tons of GPU demand and not enough capacity from TSMC. And, I think we're starting to already see a rise in the demand for CPUs, as we've heard from like Lisa Su and others saying that they're surprised that their hyperscalers are actually, the demand for CPUs has increased, not just CPU cloud cores, but actually related to AI. I think we will continue to see pressure on CPUs because at the end of the day, if you think about it, agents, it's like having 100 interns at your disposal. If you hired interns at your company, what do? You give them a laptop. It has a CPU in it. You say, go do some work, right? So this is conceptually the same thing. So we'll continue to see compute or CPU-based compute TAM increase and demand increase. So I'll let you carry on, but I think that means, to your point, that we need less of just an off-the-shelf CPU and more about I think we'll continue to see an evolution of how do we evolve these CPUs as the workloads and the demands on the AI processing, generative AI era increase.
Yeah, absolutely. And, because of all of the stuff you just explained, there's people already warning about upcoming CPU crunch. I'm like,
exactly.
Where in the AI, universe is there not a crunch? There is a crunch for lasers. There is a crunch for memory. There's a crunch for CPUs, GPUs, packaging. So nobody should talk about SSDs. Nobody should talk about shortages anymore. Everything is in short supply. It's not news. Okay.
Yeah.
Everything's in short supply.
Totally.
Anyway, now that you mentioned SSDs, we need to talk about a little bit of that stuff. But before that, this Vera CPU actually has LPDDR support, but it's in 12 SOCAMM slots, which means that it's not soldered onto the board, so you can upgrade it. So if you throw in like 128 gigs on each SOCAMM slot on the CPU, you'll get 1.5 terabytes of LPDDR memory that the CPU can use, which is awesome because the last generation had like 480 GB and it was soldered. You couldn't upgrade it or anything like that. So that is a very big and very important feature because now you have so much storage that is possible on the CPU DRAM side. So why is that so important? Now, here's the thing. When you're doing inferencing, okay, and you want to have a long context window, you're going to, for every token you generate, you're going to keep piling up on the KV cache, the key value cache. And this key value cache grows really fast. And the longer your context window, the bigger your key value cache. Now, HBM, we just spoke about. Everything is a shortage in HBM. You cannot have enough HBM, okay? Like, we will talk about it, but, in the Rubin GPU, you have an 88 GB of HBM4. That's all you've got. But that's not enough for KV cache. KV cache can grow really big if you have very long context, right? So the beauty of having DRAM in the form of LPDDR on the Vera CPU that can go up to a terabyte is that you can offload this KV cache to the DRAM. And you might think, wait, that's terrible because we need to, get it back quickly, right? But the thing is that the chip-to-chip bandwidth between the CPU and GPU in this Vera CPU is like 1.8 terabyte per second, right? So that's 2x faster. So 900 gigabyte per second was the last generation bandwidth. And now you have double the bandwidth. So what that means is that the GPU can really quickly offload its KV cache into DRAM on the LPDDR5 and keep it there and bring it back if it wants to. Now, the question is what happens if the KV cache gets even bigger than you can store on 1.5 terabytes? And we'll get to that point later.
Yes.
The one additional feature the CPU adds is that it actually encrypts the data and it provides what is called confidential computing support. And that's important because, like you were saying, unless you have your own DGX station at home where you're like confident that nobody else is going to be on it, you are renting GPUs and renting hardware. And if you're doing sensitive movements of like data within this compute system, you need that to be encrypted. And that provides security for many applications like medical and military and things like that. So that feature is introduced here for the first time. So you can see how the AI ecosystem is really getting polished now for like general enterprise use. Because right now it was all like you just kind of raw, but now it's getting the sheen on top. That's awesome. So yeah, we can go on to Rubin GPU now because it's kind of well known by now in the sense, but it's built on TSMC 3 nanometers. And it contains like 336 billion transistors. And it's like the reticle size is like 2x that of a reticle. So it's like a big chip. It's a really big chip. You can see Jensen holding it up anywhere you find the Jensen picture, he's holding up these GPUs. And the interesting thing is that it holds 288 gigabytes of HBM4 this time. Okay, and HBM4 is important because of its extended bandwidth. But if you have been tracking this memory, levels, you'll be like, wait, wasn't the GB200? Wasn't the GB300 also 288 gigabytes? Because yes, it is, but it was 288 gigabytes of HBM3E, and GB200 was more like 192 GB of HBM3E. So the difference in going to HBM4 is that instead of 1024 pins, parallel lanes, where you can pull data in and out of the HBM memory, HBM4 gives you 2048. It has double the number of interface lines that allows much, wider but slow motion of data. So it provides a total of like 22 terabyte per second bandwidth, and which is fantastic because now you're cutting down the memory bandwidth problem, the memory wall issue even more, breaking down that wall. So all of this stuff is kind of the Rubin GPU, and is supposed to give like X what Blackwell can give on inference and 3x on training. And most interestingly, at least I found this interesting, was that Jensen explained something about the NVFP4. And maybe this is well known. It's just that maybe I don't know it, but it's the whole idea of this numeric format is that they dynamically decide within the whole inference and compute system which part of the compute should use which numeric precision. So where you want to use more numeric precision, where it matters, you use more. Where it doesn't matter, you use less. So what ends up happening is that it's much faster for inference. So even though you don't like double the hardware by doing things like this, you can squeeze like 5x inference bandwidth compared to Blackwell. So they're proposing like, oh, this should be the industry standard now. But I thought that was cool. What do you think?
Yeah, it's super cool. I love these optimizations to come in later and say like, okay, we made it beefy, and how do we make it faster? Let's use interesting optimizations.
Yeah, absolutely. We should go back quickly to what context memory storage means and why that's important for long context inferencing, because that has created kind of ripples in the industry now. Although I'm not sure why this is such news, because we've always known that we needed more storage. Okay. But I'll connect the dots now and we'll see how this goes through. So the whole context memory storage is that now we know how we spoke about 1.5 terabyte per second of DRAM in the Vera CPU. Cool, but what if we need more, right? So this platform is going to treat storage as a first-class citizen. So which means that we want another system outside of CPU or DRAM where we can offload even more KV cache, even bigger KV caches, so that maybe we can one day hold the entire Library of Congress in context and ask questions to it. That's fantastic, right? And the way this is done is that it is done through the Bluefield DPU4, the data processing unit, generation 4. This actually was an acquisition. This tech was acquired from Mellanox in 2020, actually. This is not, the Bluefield was a Mellanox thing. But what it does is it's basically a network card, a CPU, and a PCIe switch all rolled into one. Because if you have to kind of go between these things, it introduces latency. So the DPU kind of rolls everything into one. And what it makes the CPU and the compute system believe is that even if you have a bunch of flash array disks, like NVMe SSDs or something, living far away, like 20 meters away from your chip that actually needs the data from that NVMe, the Bluefield DPU can make the compute believe that it is attached locally to that GPU or CPU. So it can get information really quickly based on that, right?
Yes.
And each of these Bluefield DPUs is ridiculous. It has 150 terabytes attached to it. And what that translates is that to each GPU now, you end up getting, at the superpod level, each GPU gets an extra 16 terabytes of storage where it can go and store its KV cache if it exceeds the 1.5 terabyte of LPDDR on the DRAM side of the chip. So now you can store so much more, right?
That's awesome.
Yeah, this is awesome.
Yes. And, for listeners, like zooming back out a little bit, when you think about the DPU, just think about putting extra compute in the network. That's how I think about it. Oh, so, and why would you want compute in the network? Well, you have to ask yourself, what is the GPU doing that I could offload? At the end of the day, we want the GPUs just to crunch matrix multiplications as much as possible. We don't want the GPU to have to deal with any networking stuff. And then you can say, okay, well, shift that to the CPU. Sure, totally. The CPU is going to have increasingly more things it could do. Would it make sense to take even some of that network processing and actually put it in the network with the DPU? So now you can do lots of things in the network with the DPU. Maybe this is actually where some of the security stuff comes in, which is just like, oh, hey, Vic is trying to do something here. Look up this user. Like, Vic doesn't have permission here. Don't even let it hit the CPU. Maybe you can just tackle that in the network. And this example of fast memory storage is also an example of, caching is not a new thing. We've done it in CPUs forever, L1, L2, L3. When we now start to think of the AI supercomputer as a system with a GPU and a CPU and network cards, of course, and then of course, networked storage that's very slow. Of course, it makes sense to say, could we put another intermediate storage level here of caching where we have access to lots of cheaper memory, but we try to make it faster than network storage? And then that's where the DPU comes in. You say, oh, wait, we've got some compute in the network. Maybe that DPU can help reduce latency by just knowing that, like, hey, I don't need to do all the handshakes that I normally do with network storage, or maybe I can skip certain things that normally you would do. And that's where this whole context memory storage inference platform comes in. And that's why it's both important to have a rack of SSDs that can be essentially allocated to each GPU as a new level of storage, but also to have a DPU with it, because the DPU is very important in helping make this rack of SSDs look like it's sort of an intermediate storage layer between like your CPU's DDR and then the network storage. And so this, on the one hand, it's like, this is just caching. It's not a big deal. It's just at a level of abstraction higher at the AI system, the AI cluster. On the other hand, it's very cool how they use the tools they have at their disposal, including the DPU, to actually pull this off. And of course, all of a sudden, all the SSD investors went, yes, first class citizen, people are going to buy more SSDs so that we can unlock more interesting AI by having access to really long context.
It's hilarious. Like SanDisk went up like 25% because Jensen said SSD. I mean, the concept is not new. Like you can go look up a Supermicro, just a bunch of flash, JBOF, right? JBOFs. And you go look at that, you'll find a Bluefield DPU3 in it. So this is not a new thing. Like it's already there. Like just because he says DPU4 and it's important, and we're going to its flash is important. All this hardware and tech exists, has existed for a long time. But because Jensen says NAND, everybody's now buying NAND. It's funny.
You're not wrong. I mean, I remember, Jensen talks about quantum goes up. Jensen talks about optics goes up. Jensen talks about NAND goes up.
NAND goes up.
Jensen's golden touch.
Yeah, the whole idea of context memory storage is not these disks don't live within the NVL72 rack. So he shows this in the keynote. He shows like the entire SuperPod and all these racks, and he walks all the way to the other end. There are like two little racks there. I don't know if it's both or just one of them is the context memory storage. One of them is just a bunch of flash with a Bluefield DPU in there. So yeah, so it's not like it's going to be within the NVL rack. It's going to be its own separate rack, this storage thing. So yeah, after this, I just had like a couple of odds and ends that stood out from this whole NVIDIA presentation to me. I think one thing I really like is that it reminded me of, when Jensen showed the inside of the rack, the Vera Rubin rack, and he's like, look, there are no cables in here. And he's like, look how it just clicks fit, and everything just clicks into place. It's awesome. It reminded me of Elon's, the SpaceX rockets, the jet engines, where you have like the Falcon engine 1, 2, and 3. And you see like every generation, it has gotten slicker and slicker and with fewer complicated wires and messy stuff. It's become more streamlined. I see the same thing happen kind of in the server rack space now.
Yeah, super interesting. Yes, I've seen this with Rivian too, where Rivian, SpaceX, I'm sure Tesla was the same way. It's like first you make it work, and then in the next generation, you ask, like, how can we reduce the components, make it more manufacturable, make it more reliable, make it easier to service? And
Yes.
obviously, Jensen and team are at the place where they can spend a lot of engineering effort on that.
He mentioned that it takes 2 hours to assemble the previous Grace Blackwell series with all these cables, and now it takes 10 minutes
Amazing.
to just clip things together. And I think one interesting thing, again, because whatever Jetson just does seems to move semiconductor market so much. When he says no cables, I think the investing world heard cables and they just ran and did something to the first cable company they could think of, which seemed to be Credo, which is weird because Credo does not deal with internal to the rack cabling. They do external to the rack cabling. Internally was more like Amphenol and things like that. But it's been known for a while that Rubin series is going to drop a lot of cables, and because they went to this mid-plane PCB assembly that removed a lot of cables. So this is news for a long time. But the moment Jensen says cable-less design, Credo stock drops. It's so funny. It had nothing to do with it.
This is the argument for people to read your Substack and my Substack and actually understand what is scale up, what is scale out.
Yeah.
So that, because you can just look at that and say, buying opportunity. A bunch of people don't understand and they sold, and actually nothing has changed here.
Yes. Nothing has changed. Yeah, there was a little scare about the coolers too, because Jensen said that you could cool these chips with basically warm water at 45 Celsius, which means that even in the hottest temperatures, you could run data centers and not have chillers. That's why the 45 Celsius, because you can run this data center in a desert and, the temperature is going to be warm enough. So it'll take out the heat and recirculate. So there's no need for chillers. I looked this up too. The Hopper series seem to have chillers, but ever since the Blackwell series, it's kind of become optional because it had this warm water thing anyway. But now you don't need chillers. And so I think there's another little flurry of activity there. But I think some of all of this stuff is known to the people who are deep in the weeds on this kind of stuff.
Yes,
so,
interesting. Yeah, chiller sell off. Oh no. But
chiller
yeah, to your point.
sell-offs.
Yeah, just get into the weeds and understand so that you know reality.
The one thing I did not understand, even though I'm deep in the weeds, is whether the NV Switch 6 is actually 400 gig, because Jensen's slide said 400 gig. And I did not know whether it's a single lane, which is really interesting because think about that, right? If it is 400 gig single lane, that means that the scale up in the spine, which is fully copper, is going to run at 400 gig single lane, which is a lot. That tells me that copper still has a lot more life before we have to go to optics for scale up. If it's running 400 gig single lane on the NVLink spine, I don't know. I tweeted about this and people were like, no, I think it's 200 gig, but bi-directional. Oh, okay. Maybe I got tricked by Jensen math and cute robots. I mean, I don't know what it is though. I still haven't been able to find out. So if anybody listening knows, let me know or let us know.
There you go. Yeah. You'll have to reach out to NVIDIA and ask for clarification there, because it is interesting. But that has definitely a lesson that I've learned over the years, which is unfortunately, everything you read from every company, they put a number up, but then you have to scrutinize it and ask, what does this mean? Which is a little bit too bad that we're not in the world where we can just believe what's written, but
yeah.
That is marketing. I understand the pressure to always feel like numbers are going up, because to your point, you say cableless, people sell cable companies. And so you can see where if people numbers didn't go up, sell,
Yeah.
But it's
exactly.
I don't know, let's be intellectually honest here and just explain things.
Yes. I mean, that's what we try to do. We try to look at this through a harsh lens on our Substack and be go on through all the depths of stuff and see, is it single direction or bi-directional? What is this? What is that? I mean, this is what we spend our time doing. And I think we love doing it. So don't get us wrong here. We love it.
Oh, for sure. For sure. Yeah. So fun. So yeah, any final takeaways from NVIDIA at CES?
No, I think it's exciting times. I think NVIDIA stole the show. I did watch AMD's keynote also, and it involved a lot of people coming and talking about how they're using NVIDIA products. And they did talk about the MI, 450. Yeah. So it wasn't fancy. after that, watching Nvidia, I was expecting Lisa to like open up and show us the MI series of inference training, all that. Nothing happened. I was kind of disappointed. So I guess like Jensen kind of stole the show.
Yeah, we'll have to talk more about AMD sometime. I mean, maybe Lisa was treading the consumer electronics line a little bit more.
As she should in this show.
Totally. I would say on the AMD front, really quick, of course, it was awesome to see Fei Li up there talking about her company and world models. She wrote a book, I think it's called like The World's IC or something like that, autobiography. Super awesome, highly recommend it. And then the one thing that stood out to me really quick from AMD was they had a new offering. They didn't talk about it much. MI 440, I believe it was called. And it was like enterprise grade, and it was just a server node, so maybe like 8 GPUs. And again, this aligns with a lot of what we've been talking about of having a portfolio of compute options for people, because not everyone needs, tens of racks or hundreds of racks. And actually this does align with, you have to ask, okay, where's that enterprise server going to go? And it might very well go on-prem. And so it continues to align with the idea of like, how do we bring as much super compute to the enterprise as possible at price points that fit? And yes, it is about the cost per token, so that we, in some sense, so that we can run agents and it doesn't cost hundreds of dollars, it costs tens of dollars or single dollars. On the other hand, for a lot of these enterprise buyers, they have a fixed budget. They have $5 million to spend this year, right? And so while the cost per token matters, it kind of doesn't. It's just like, maybe I have $1 million. Can I get this AMD 440? It's air cooled, maybe, I don't know. And I can fit it in my closet at the headquarters, but that still enables our company to do a lot of really interesting AI enabled productivity boosting things. So I'll just leave it there, maybe teaser for another time, but we continue to see whether it's DGX stations or AMD trying to bring the AI compute closer to the desk. And that is very interesting.
Awesome. All right, let's call that the episode. Great chatting with you. CES had a lot more stuff other than just NVIDIA's keynote and all that hardware that we spoke about here. But, we don't want to spend all day talking about all of CES. So maybe we'll intersperse all these discussions from CES in all the episodes we talk about for the rest of this podcast.
There you go. Sounds good. Yes. Thanks, Vix. Thanks, listeners. We'll see you next time.